In this section, we'll be talking about operations on matrices, and as such, let's consider that matrices don't always come from systems of equations, because certainly they don't. Little notation here. We can designate a matrix using the entries in the matrix like this. We can call it by some kind of name using an uppercase letter, or we could designate the matrix entries like this. Now notice A is the lowercase of the A right here. The IJ refers to a row column kind of thing. If we're talking about A subscript 1, 2, then it would be the item that is in the first row, second column. So first row, second column would be 7. Now the notion of equality and the notion of addition are just about exactly as we would expect them to be. Equality occurs when we have the entries in a second matrix would be exactly the same as the corresponding entries in the first matrix. So we would have another one that looks just like this, and therefore the matrices would be equal. The idea of addition is about the same as we would expect it to be as well, because all we do is add the entries in corresponding positions. To add these two matrices, we're saying 4 plus -1, that's 3. And then -1 plus 0 is -1. 5 plus 3, 8. And then up here, 7 plus 2, 9, and 3 plus 5, 8, -2 plus 4, 2. Okay, so that's the idea. Now, with multiplication, there are actually two kinds of multiplication. The first one is very predictable. It's called scalar multiplication. It works like this. Suppose we have matrix A defined this way. For scalar multiplication, we multiply times each item within the matrix. 2A means 2 times the entries here for the matrix, and so we just double all of them. 2 times -2, -4, 2 times 1, 2, 2 times 3, 6, 2 times -1, -2, 2 times 0, 0, 2 times -4, -8. Highly predictable kind of thing. Now with this idea, we can actually write expressions and simplify expressions in this matrix format. If this is matrix B, then we can evaluate or simplify 2B minus 3A. And we do it like this. 2B means 2 times matrix B, that's from up here, minus 3 times A. Well, matrix A is the one from over here. And now we do this scalar multiplication business, double all of these entries, and we get these. Now when we slide over here, we actually have two techniques that we can use. Minus 3, you see it's minus 3 times this. Now I've elected to take the technique where I'm going to multiply 3 times all of these, and then write minus, you see, 3 times all of these. The other technique would be to say minus 3 times all of these and add the two matrices. Whichever way you'd like to do it is okay. But again, I'm doing this. I'm saying, okay, it's easier for me to multiply 3 times all these entries. And then it's easy for me to subtract down here rather than add. So I'm thinking of it this way. 3 times -2, -6. 3 times 1, 3. 3 times 3, 9. 3 times -1, -3. I'm sure you get the picture. Now we have minus between these two, and we subtract corresponding entries. So we would have 0 minus -6. That's 0 plus 6, or 6 for that entry. Then 4 minus 3 is 1. Then -8 minus 9. -8 with -9, that's -17. And then, let's see, 6 minus -3, that's 6 plus 3, 9. Then 0 minus 0 is 0. And then -2 minus -12, that's -2 plus 12, or 10. Okay. Since we can deal with expressions involving matrices, maybe it's not surprising that we could solve equations involving matrices. Now here, we want to solve for x. We have this equation. There are a couple of ways of proceeding here. We could actually divide through by 2 and have x isolated over here, and then deal with the 2 in a particular way over here. That might be pretty easy, actually. I've elected to just take this expression and simplify it as much as I can. So we have 2x equals 2 times a, and the a is from before, and then minus the b from before. You see, and now 2 times this using our scalar multiplication. Subtract this, we bring it down, so now we subtract corresponding entries. And just as an example, -4 minus 0 would be -4. Then -2 minus 3 would be -5. And so on to get all of that business. Well, now we have 2x is equal to this matrix. How do we deal with that? Well, we want to isolate x, so we'll divide by 2 on this side, and we divide by 2 over here. Or we can think of it as multiplying by 1/2, and I think that's a little easier. 1/2 times 2 would give 1x on the left, and then on the right we have 1/2 times all of this. So again, it's a scalar multiplication idea. So we just take half of each of these entries, and we get this as the result. So scalar multiplication, solving equations, and so forth. Now let's talk about a different kind of multiplication. The multiplication of two matrices, but it's not scalar multiplication. Here we have a matrix A and a matrix B. The first thing I'd like you to notice is that they are not the same order. Order is really important in this process of multiplying matrices. Now, this is a 3 by 2 matrix, and this is a 2 by 4 matrix. It's a 3 by 2 because we have 3 rows, 2 columns. 2 by 4 because 2 rows, 4 columns. All right, it turns out that we can only multiply matrices in which the number of columns of the first one corresponds with the number of rows of the second one. All right, and now that therefore takes out the idea of the commutative property holding when we're multiplying matrices. That is, although we are able to multiply A times B, we cannot multiply B times A, because if we swap the roles of these two, we wouldn't have this row-column correspondence idea. Okay, now, once we establish that we can multiply the two, we can identify the order of the resulting product matrix, and the order of that product is going to be 3 by 4. So A times B is going to be a 3 by 4 matrix, and we can set up the skeleton for that situation like this. Now, there are a number of ways of illustrating that and calling attention to the various entries here. One way would be, I suppose, to do this. We have 3 rows, something like this, and then 4 columns. 1, 2, 3, 4. And everywhere where we have an intersection, you see we have an entry of some kind that we would have to put in here. Well, that gets a little convoluted, so let me use another designation here. I'm going to just put some circles in here to designate the different entry possibilities in this answer matrix. So we'll have entries in these positions, and now we have 4 columns. So this is 1, 2, 3, 4. Okay, now the next trick is to identify the value of each of these that goes in each of these circles. Well, let's take this one. Now, this item is in the first row, first column of our answer. And here's what we do. Now, first row, first column. We take the first row of our first matrix and the first column of the second matrix. And we perform this operation. We take the entries here in this first row, and for each entry, we're going to multiply times the entries over there. Here's what we're doing. It is -1 times 2. I'm going to write that out for emphasis. -1 times 2, and then plus, you see, first times first, and then along this row, then 3 times 4. So we have, let's see, -2 plus 12, this is 10. So the entry that goes right here is 10. Now let's take another spot. Let's take a spot that's, maybe somewhere down here. Now notice that this item is in the, well, let's see, rows and columns, 1, 2, 3. This is in the third row, second column. Okay, this is the A subscript 3, 2, or 3, 2. Item. Let me write that a little better. Third row, second column. Now we use this information to go up here and identify, let's see, third row, boom, second column, these two. So we're taking these two entries and we're multiplying times these two entries in a particular way. It's 5 times 5 is 25, plus 0 times -3 is 0. So this entry turns out to be 25. Now, we have to do that for every single entry in here. All right, so we're kind of intertwining these two matrices in a very particular and, at first, complicated kind of way. Well, we'll go over this multiplication of matrices here, but I want to do it in the context of a problem. It turns out that by looking at this situation in terms of a business application, we can get some feeling for the usefulness of this whole process. Take a look. A company that manufactures racing bicycles has the following labor hour and wage requirements. Here's a graph of part of those requirements. The labor hour requirements. This is hours per bicycle for the entries in the matrix. Now notice the departments: cutting, assembly, and packaging, and the various models of bicycles: the basic model, light model, and ultralight models. If we want to identify a particular item, like, for example, the number of hours required for cutting a light model bicycle, we simply cross-reference within our matrix. You see, we cross-reference the cutting with the light, and we get 1.5, so it would take 1.5 hours of labor to cut a light model bicycle. Well, here are the wage requirements. Now, this is in dollars per hour. We have two plants, you see, plant A and plant B, and here are the various departments that are designated on the right: the cutting, assembly, and packaging. Well, with that in mind, we can answer these questions involved in the problem. What is the labor cost for a light racing bicycle at plant A? So we have a light bicycle at plant A. Here's what we do. We look at the hours and the wages. Now, for the hours, we identify the light bicycle, you see. And for the wages, we're talking about plant A. Now, if we want to determine the cost, we simply multiply the hours times the cost per hour. And notice that the cutting hours is 1.5, the assembly 1, and the packaging 0.4. And the cost for those are $14, $8, and $7. So, of course, what we're going to do is multiply 1.5 times 14, and then add 1 times 8, and then 4/10 times 7 to get the total cost. Well, performing these operations, we find that the cost is $31.80. Now let's suppose we want to find the labor cost for an ultralight bicycle at plant B. Well, again, all we do is a kind of a cross-reference here. We take our hours matrix and the wages matrix, and we identify the components that we're after. We're talking about an ultralight at plant B. So again, we'll multiply the hours times the wages, you see, for each of the departments: the cutting, the assembly, and the packaging. And here it'll be 3.5 times 12, and then 3 times 7, and then 0.5 times 6. And the result, $66. Now we're ready to answer this question, the most important. Compute S times T. Now, S and T represented our two matrices, and it says interpret the result. Well, here's what we do. We set them up like this. Here's S, and here's T. And we first of all look at what kind of matrix we have. We have the row-column idea. You see, we have a 3x3 matrix for S and a 3x2 for T. So we know that S times T will turn out to be a 3x2 matrix. Now, as a result, we set up the structure for a 3x2 matrix for our answer. And here are the different parts involved in the S times T, or the ST matrix. Now, for the entry in each position, we look at that entry and we decide what entry that is. Where is its position in ST? This item is in the first row, first column. And what that tells us is that we're going to multiply the entries in the first row of S times the entries in the first column of T. So here we would be multiplying 0.9 times 14, and then adding 0.8 times 8. and then 2/10 times 7. The result then is 20 and 4/10, or 20 and 40 hundredths for that entry. Now each of the entries is calculated in the same way. Consider an entry in this position. Now notice what position this is. This is the third row, second column. So what we'll do is multiply the entries in the third row of the first matrix times the entries in the second column of the second matrix. So in this case we're talking about 3.5 times 12 plus 3 times 7 plus 0.5 times 6. And the result gives us the entry in this position, 66 in this case. Now all of the entries in our resulting matrix are figured the same way. That is, we look at the row and the column involved in the entry. We multiply along the row in the first matrix and along the column in the second matrix to get the entries. The entries look like this. Well, let's interpret what this means. Remember now, our first matrix, the S matrix, involved it was a 3 by 3 matrix, and the rows were the models involved with our bicycles, the basic and light and ultralight models. And the columns were departments, cutting, assembly, and packaging. Now, what about the 3 by 2 matrix, the T matrix that we talked about? Well, the rows were the departments, the columns were the plants. And when we multiply the two matrices, this is what happens. We get a result which is models by plants. That is, the rows become models and the columns are simply the plants involved. So that's what we have here in this resulting matrix. Let's set it up this way. The rows are the models and the columns are the plants involved. Now the numbers, the entries in the matrix, are simply this. These entries represent the labor costs for each model of bicycle at each plant.